this class, we'll talk about the algebraic interpretation of the simplex method. So before we start to set up the model, let's first introduce some concepts. We say to start a simplex method, we first need to introduce the select variable. So the select variable is a variable we introduce to make a constraint, usually in our linear programming problem, an inequality to an equation. For example, if we have the constraint that x1 is less than or equal to 4, then we can define the select variable to be the difference between the right-hand side and left-hand side of the inequality. That is, we set x3 equals 4 minus x1. By doing this, we say x3 is actually the gap or the slack between the left-hand side and the right-hand side. So moving the variables around will obtain x1 plus x3 equals 4, and our original inequality constraint, x1 less than or equal to 4, becomes a pair of constraints. One is the equation x1 plus x3 equals 4. The other is the non-negativity, x3 is bigger than or equal to 0. So with this idea, we can change our linear programming problem where all the constraints are of the less than or equal to form to equations. For example, if again we have this problem with all these inequality constraints, we say by adding each inequality to the left-hand side, a select variable, we have x1 plus x3 equals 4, 2x2 plus x4 equals 12, 3x1 plus 2x2 plus x5 equals 18. Now with this, we introduce one select variable to each inequality and make all the inequalities equations. And we'll see how these equations perform helps to our simplex method. Okay, so next, this idea of the select variables actually give us the concept of the basic solutions. Notice from the augmented form of this example, we have the system of functional constraints. It has 5 variables and 3 equations. So that we have the number of variables minus the number of equations is actually 2. So the number of variables is more than the number of equations. This gives us 2 degrees of freedom in solving the system. And in the simplex method, we usually set these 2 free variables to 0. And then after setting all these variables, these 2 free variables to 0, these 0 variables are usually called the non-basic variables. And then we can solve the system of equations with 3 equations and 3 variables. After finding the simultaneous solution, they are usually called the basic variables. We obtain the basic solution. The basic solution has the following properties. First, we say each variable is designated as either a non-basic variable or a basic variable in the system. Second, we say the number of basic variables equals the number of functional constraints. The number of non-basic variables equals the total number of variables minus the number of functional constraints, as we defined earlier. Third, the non-basic variables are always set equal to 0 in our simplex method for convenience. Last, the values of the basic variables are obtained as the simultaneous solution of the system of equations. And this set of basic variables is often referred to as the basis. And then we say if the basic variables satisfy the non-negativity constraints, the basic solution is also a basic feasible solution, which is called BF solution in short. And from the geometric interpretation, we can actually check that a BF solution here in the augmented form is just the CPF solution from the geometric point of view. With the idea of the BF solutions, we can actually interpret the simplex method as an iterative algorithm with the following structure. First, we start the initialization by finding an initial BF solution. Next, with this initial BF solution, we do the optimality test. If the current BF solution is optimal during our optimality test, then the simplex method terminates, and then we find our optimal solution. If no, if it doesn't pass the optimality test, we do the iteration and find a better BF solution, and then again do the optimality test until we find an optimal one. Let's look at an example of how algebraically the simplex method works. So to start the simplex method, as we said, given a system of linear programming problem with all the constraints, we first need to put all the inequalities to equations by introducing slack variables. So by introducing slack variables, we have x3, x4, x5. And now we say, usually in the simplex method, we choose the decision variables to be zeros, to be non-basic variables for the initial BF solution. So after setting x1 and x2 equal to 0, the values of x3, x4, x5 can be read directly from the right-hand side of all these equations, 4, 12, and 18 respectively. Next, for the optimality test, basically we just need to check if the objective function is optimal or not. So the objective function z consists of two variables, x1 and x2. We say, well, their coefficients are both positive. So x1 and x2 were the non-basic variables. They were set to be 0. But now, since their coefficients are positive, increasing the values of x1 and x2 will give us an increase in the objective function z. So in this case, we say, since increasing the values of x1, x2 will give us an increase in the value of z, at this point, by setting x1, x2 equal to 0, the solution is not optimal. So we have to start our iteration. During the iteration, the first thing we need to do is to select. Since we can increase both x1 and x2, we want to check whether we should increase x1 first or increase x2 first. If we increase x1, increasing x1 by 1 unit, the value of z will be improved by 3 units. On the other hand, if we increase x2 by 1 unit, since the coefficient of x2 is 5, increasing that by 1 unit, the value of z will be improved by 5 units. Apparently, increasing x2 will be more efficient. So in this case, we choose x2 to increase. Okay, so at this point of the simplex method, at this step, we choose one variable to increase from 0. Since this variable is increased, its value is not 0 anymore, it's not a non-basic variable. And in this case, it changed from a non-basic variable to a basic variable in the next BF solution. And because of this process, this variable is usually called the entering basic variable because it's entering as a basic variable for the current iteration. So in our example, we choose x2 to increase, then x2 is our entering basic variable. Okay, so then the next question is, we decided to increase x2, but how far we can increase it? Of course, increasing x2 will increase z, so we would want to increase x2 as far as possible. However, we cannot increase x2 indefinitely because x2 is bounded by some constraints. By looking at these constraints, we can see that x2 and x4 and x2 and x5 has some relations. Since here we don't do anything to x1, x1 is still set to be 0, then we can solve x3, x4, x5 in terms of x2. With all these expressions, we say, well, they are the slack variables. They must satisfy the non-negativity constraints. So the first one is x3. This is equal to 4. It has nothing to do with x2. So there's no restrictions on x2 for this part. On the second one, we have x4 equal to 12 minus 2x2. But it has to be non-negative. So x2 cannot be too big. It has to be less than or equal to 6. Also, for x5, we play the same game. We say x5 is also non-negative. By expressing it in terms of x2, we have x2 is less than or equal to 9. So this says that increasing the value of x2 will decrease the values of x4 and x5, but they have to be non-negative. So x2 can be increased as far as to 6. At this point, when x2 reaches 6, x4 will be 0, and it can't be decreased anymore. So in this method is what we call the minimum ratio test, as we simply compare the ratio of the constant term in the equation and the coefficient of x2 and pick the minimum one. Okay, so at this step, we use the minimum ratio test to determine which basic variable drops to 0 first as the entering basic variable is increased. And of course, decreasing the basic variable to 0 will convert it to a non-basic variable for the next BF solution, as we defined a variable equal to 0 is a non-basic variable. So in this case, the variable changes from a basic variable to a non-basic variable, and this variable is called the leaving basic variable for the current iteration. So in our example, x4 is the leaving basic variable. Next, we decided that in our initial BF solution, x2 equals 0, x1 equals 0, they're the non-basic variables. In our new BF solution, x2 equals 6 is a basic variable. Then the non-basic variables are x1, x4, both equal to 0. In our old BF solution, by reading from the right-hand side, we can read the values of the basic variables directly 4, 12, 18 for x3, x4, x5. However, in our new BF solution, we only determined that x2 can be increased to 6. How about the values of x3 and x5? It's not very straightforward by setting x2 equal to 6 to solve for x3 or x5. So at this step, we say we need to perform an extra step in the iteration. The purpose of the next step is to convert the system of equations to a more convenient form for conducting the optimality test and for the next iteration with this new BF solution if needed. This is our original system of equations, the constraints. And then what we want to do in the process will also identify the values of x3 and x5 for the new solution. What we want to do to the original system is to apply elementary algebraic operations, or in terms of matrices, the Gaussian elimination, so that the coefficient of x2, our entering basic variable, will have the pattern of the coefficient of x4 with 0, 0, 1, 0. If we read all these equations from 0 to 3, we can see the coefficients of x4, 0 because there's no x4, 0 and 1, 0. Now we want the variable x2 has coefficients with the same pattern. How do we do that? We say there are basically two types of elementary algebraic operations. The first is to multiply or divide an equation by a non-zero constant. The second is to add or subtract a multiple of one equation to another equation. If we look at our original system of equations, we see that we want the coefficients of x2 to be of the form 0, 0, 1, 0. Equation 1 has nothing to do with x2, so the coefficient of x2 is 0 automatically. For equation 2, the coefficient of x2 is 2, so that's easy. All we need to do is to divide both sides by 2, and then we can change that variable, the coefficient of that variable to 1. On the other hand, if we look at equation 3, we have this 2x2. So to eliminate that 2x2, we can simply do equation 3 minus equation 2, and then to get rid of that 2x2, and then we can get a new expression for equation 3 that is without x2. Similarly, for the same reason, since equation 0 also contains a negative 5x2, we can multiply our equation 2 by 5/2 and then add that to equation 1 to get rid of this x2. After we do all these elementary algebraic operations, we got a new system of equations While here, we get rid of x2 except in the equation 2. The coefficient here for x2 is 1. And after we do that, what's the benefit of doing that? Recall that now our non-basic variables are x1 and x4. They both equal to 0. Now, from this system of equations, we can read directly that, well, x1, x4 equals 0, so z equals 30, x1, 0, x3, 4, and then x2, 6, x1, x4, 0, and then x5, 6. By doing these operations, now all these variables, z, x3, x2, x5, the values of them can be read directly from the right-hand side. So this is the benefit of conducting such row operations. Okay, so now we have the new objective function z equals 30 plus 3x1 minus 5 halves x4 with the new BF solution. Next, we just repeat the optimality test again. So in this objective function, we can see that the coefficient of x4 is negative. So increasing x4 will decrease the value of z. That's not what we want because we want a maximum z. However, since the coefficient of x1 is positive, increasing the value of x1 will give an increase in z. So still, we say at this point, our objective function is not optimal. We need to conduct the simplex method again first by applying the minimum ratio test to determine how far x1 can be increased. So again, look at all these constraints on x1. So the first equation has x1 and x3. Since x3 has to be non-negative, x1 has to be less than or equal to 4. The second equation has nothing to do with x1, so x1 has no bounds here. And then the third equation also contains x1, since x4 is 0, and then x5 is also non-negative. By calculating the inequality, we see that x1 has to be less than or equal to 2. Again, x1 cannot go too far because we want all the variables to remain non-negative. So at this point, we say x1 can be increased up to 2. And then increasing x1 means x1 is the entering basic variable. And since now x5 decreases to 0 first, x5 is the leaving basic variable. So again, we perform the elementary row operation hoping to make the coefficient of x1 follow the pattern of the coefficient of x5 because one is entering, the other is leaving. So what's the pattern of the coefficient of x5 in our system? 0, 0, 0, 1. So again, we conduct the basic elementary row operations so that we can make the coefficient of x1 follow the same pattern. After we do it, again, now we have x4 originally is a non-basic variable. x5 is the leaving basic variable, so it's also non-basic at this point. By doing such operations, again, we can read the values of the basic variables and our objective function directly from the system. Z equals 36, x3 equals 2, x2 equals 6, x1 equals 2. And then, from this objective function, we see that since now x4 and x5 are on the left-hand side, increasing their values will decrease the value of z. So that's not what we want. So at this point, we cannot increase any of the variables any further. At this point, by the optimality test, this solution, this BF solution is our optimal BF solution. And then we say the simplex method terminates. Okay, so this is the algebraic idea of how to conduct the simplex method. Next time, we'll introduce a more convenient way of doing simplex method in the tabular form.